Welcome to qnawire.
We'll first write down the value of the gravitational constant g times the mass of Earth. So gm for the Earth is equal to the gravitational acceleration at the Earth's surface times the radius of Earth squared. And so this is equal to 9.81 times 6.37 times 10 to the power 6 squared. And so this value is 398.06 times 10 to the power 12 meter cubed per second squared. We'll find the same value now for the sun, and we'll use these values a little later on. So the GM value for the sun, GMS, is equal to 332.8 times 10 to the 3 times the value GM on the Earth. And if we multiply this value by our first answer there, we get this value to be 132.474 times 10 to the 18 meters cubed per square second. Now, the first thing we'll do is look at the circular orbit of Earth. And this is the circular orbit of Earth about the sun. So the orbit of the Earth from the center of the sun is at 149.6 times 10 to the 6 kilometers, which is 149.6 times 10 to the 9 meters, 10 to the 9 meters. And so what we'll do here is calculate the speed of this orbit, VE. So VE is equal to the square root of G times M for the sun over the radius of this orbit. So we're trying to calculate the speed of Earth's orbit about the sun. And if we substitute our values in here, we get this to be the square root of 132.474 times 10 to the 18 over 149.6 times 10 to the 9. So remember, the sun is responsible for the Earth's orbit, or the mass of the sun is responsible for the Earth's orbit. And this value is 29.758 times 10 to the power 3 meters per second. Now that's the speed of the Earth as it orbits the sun. Now for our spacecraft, we have a transfer orbit. And that transfer orbit is from Mars to Earth. So that's transfer orbit AB. We know that RA is equal to RE. So it finally comes to a position where its orbit is the same as the orbit of the Earth around the sun. So it's moving from the Mars to the sun. Or Mars to the Earth, sorry. And RB is equal to RM is equal to 227.8 times 10 to the 9 meters. So the speed of the orbit at point A is equal to VE plus the transfer velocity, which we'll call delta V subscript A. So the transfer velocity in moving to point A. And this is equal to 29.758 times 10 to the 3 plus the transfer velocity is given as 2.94 times 10 to the 3. Both are in the same units, SI units. So we get the speed of the orbit at point A to be 32.698 times 10 to the power 3 meters per second. And with this value, and looking at the conservation of angular momentum, which tells us that m times RA times VA must equal to the mass of the spacecraft m times RB times VB. So we can see from here that we can rearrange this and solve for velocity at point B, or in orbit B. VB is equal to RA VA over RB. And we have these values, so we can substitute them in. So this is 149.6 times 10 to the 9 times 32.698 times 10 to the power 3, that's RA times VA, over the radius of the orbit at B, 227.8 times 10 to the 9. These again all in SI units. So we get VB to be 21.473 times 10 to the 3 meters per second. Now we'll do a similar thing for the orbit, the circular orbit of Mars. So this is the orbit of Mars about the Sun. And we assume that this orbit is roughly circular. So Vm, the speed of the orbit of Mars about the Sun, is equal to square root of g m value of the Sun divided by the radius of Mars' orbit about the Sun. And again, these values are known. So that's the square root of 132.474 times 10 to the power 18 over 227.8 times 10 to the power 9. Hence we get Vm to be 24.115 times 10 to the power 3 meters per second. So we want to calculate the increase in speed required at point B. So the speed increase that is required at point B, we'll call it delta V at point B, is equal to the speed at Mars minus the speed at B. And this is equal to 24.115 times 10 to the power 3. Remember, these are in the same units. Minus 21.473 times 10 to the power 3. Hence we get delta VB to be 2.643 times 10 to the 3 meters per second. So this is actually 2 0.64 kilometers per second.